incredibly flat in appearance. Just incredible. In this presentation, I will show you all the gory details of how I derived this result. Stay tuned, you're in for a real treat. We are going to learn to see the world not only with our eyes, but with our minds. Before early 2020, I was up in the air quite often, flying to different locations in the U.S. On business, and I took advantage of those opportunities to look out the window and think. As an engineer, my brain was always active, pondering what I'm seeing. And once I brought infrared cameras on board, wow, I was just blown away. In the visible spectrum, there's always haze, even when we think it's fairly clear. But infrared can pierce through that atmospheric haze and reveal the amazing flat Earth. I initially began composing 3D images so I could study the shape of the surface. If you have color 3D glasses, these images are just incredible. But that got me thinking about how to extract this 3D data that's available in these images, and that's how I got started with photogrammetry. This graphic will help us understand how to extract the data. So the aircraft is moving along a flight path, and we know the velocity and the time difference between the two images, okay? And objects in the scene move relative to the image. So as you can see, Fargo way up there has changed relative location, those horizontal black arrows, right? It was more to the left, and then it went more to the right in the field of view of the camera. And
Hola a todos, bienvenidos al programa Fotogrametría Aérea. Aquí estamos con el gran J.T. Dolan. Y bueno, acá está hablando del campo de visión de la cámara, ¿verdad? Eso también está incluido en la perspectiva que vimos en el video pasado. Es decir, que la perspectiva incluye el punto de fuga, que sería la profundidad, y luego los ángulos de visión, que sería el marco 2D, ¿verdad? El eje X y el eje Y, hacia arriba, ¿cierto? En altura. Y ellos sacan una diagonal, ¿cierto? Desde la esquina en diagonal, ¿cierto? Y eso forma el ángulo de visión de abertura del lente. Entonces, más abierto es menos milímetros y más cerrado es mayor milímetro. Creo que era bueno, importante aclarar eso, porque la vez pasada no se habló de esto, entonces ahora se complementa y queda claro más allá el concepto de perspectiva. Por ejemplo, si alguien te habla de paralaje, ya sabes lo que es por el video pasado, y si te hablan de perspectiva, ya también sabes lo que es ahora por complementando estas dos cosas, ¿cierto? Porque este concepto que estamos viendo ahora no tiene nada que ver con paralaje, es solo de perspectiva. Entonces ahí hay otros puntos donde se suma esa diferencia.
That motion can be translated to angles because we know the focal length of the camera, etc. Now we can also get
La distancia focal es lo que tiene que ver con los milímetros, ¿verdad?
the baseline distance D at the bottom because we know the time difference between the photos and the flight velocity. So we get D, and then knowing the angle phi, which is really theta 1 minus theta 2, okay, we can calculate the range R, and that's a slant range. The next graphic will make that clear. Now that's an approximation for small angles, where actually the equation I'm showing is actually for the arc length, but when the angle is small, the arc length is pretty close to the straight line distance D. So we've calculated the slant range from the horizontal movement, and then we can get the elevation angle of those features from the image and the number of pixels, etc. So now we have range, slant range, and elevation angles, and we can now calculate the vertical drop and the horizontal.
¿Se dieron cuenta lo que está haciendo? Está haciendo la distancia angular desde el avión, entonces la está viendo al revés a como la vimos en el video de distancia angular, que nosotros la vemos desde el horizonte, desde la superficie, él ahora la está viendo en altura y está tratando de ver las variaciones supuestas del globo también, al parecer.
Basically, we can get X, Y coordinates for features on the ground, which is really cool. And that's how I was able to create the chart.
Y lo más probable es que llegue, que es plano y no hay tangente en la parte de abajo, entonces no hay caída, digamos. Y esto es importante porque había gente hablando mal de que pusieron la gran estafa de J.T. Toll en un video de esa gente del orfanato y es para arruinar a buenos terraplanistas, porque él aquí te está mostrando el modelo de la cámara, todo, el sensor, todo lo que está haciendo. Mira el ángulo de edición o el campo de edición.
The 27-degree vertical field of view translates to about a 10-mile minimum distance to objects I could see. If I point the camera such that the top of the image
Ese lente
is on the
es súper buena calidad. Y un gran angular, no es un zoom. Entonces, yo no sé por qué dijeron que era una estafa.
30 and a 50, and I settled on this one. The 50 zooms in a little bit more, but objects in the distance appear
el otro lente lo usa en otros videos, pero aquí estamos con el gran angular nada más.
So we don't really gain much, and I wanted a wider,
después va a hablar de la distorsión de barril que tiene que ver con el ojo de pez.
16 is better for that, but then we kind of don't have the resolution out there.
Está hablando de cosas de la cámara, ¿no?
So I chose the 30. It seemed like a very good compromise. One of the problems with this particular lens, the Sigma on the Sony Alpha 6000, it doesn't correct automatically the barrel distortion. There's some barrel distortion there that's visible, which makes the Earth look like a globe, as you saw in the intro. And some of you may have been wondering, like, what in the world? But we'll correct for that. It's known, and it's an easy process to correct the barrel distortion. What's really neat in this part of the country, the properties are separated along.
Son distorsiones normales del lente, ya sabemos, ¿cierto? La GoPro distorsiona exageradamente, incluso ellos matemáticamente también en el sensor lo corrigen con un seteo de cámara, ¿cierto? Y acá no, pues acá no tienen ese seteo seguramente, porque se setea todo en el programa después de fotografía, entonces no. ¿Qué es lo que va a hacer él ahora? pero en el fondo él puede hacer un paneo y se ve todo plano igual, o sea, no es que haya caída de esa curvatura en ese momento en que se está mostrando, ¿cierto?
North, south, east, west, and
De hecho va
you see
avanzando
this
y sigue
grid
en el
pattern,
plano,
which is
¿no?
really cool. Makes you feel like you're
Se
watching
nota
the
que es del
globe
lente.
go by. I was going to do this with the correct images, but I said no. Let me just leave it like this.
Y
You'll
bueno, ahí
get
también
the flat
tiene
earther's blood pressure
metadata.
up a bit. Anyway, let's do more analysis. As you're aware, barrel distortion makes things look convex at the top and concave on the bottom. And there is no distortion along the middle. And that can also be an inclined line passing through the center. So we'll look at an image I've calibrated by taking different images so I can get a feel for the distortion. But I want to say that there should be a little bit of a drop or curvature because there is infrared attenuation through the atmosphere. So we should see a little bit of curvature on the horizon because we're not really seeing the true horizon. The atmosphere blocks our view. So here's the amazing result when I position the horizon.
Claro, lo que decía es que a lo más lejos ya empiezan a producirse esos efectos, ¿cierto? De eh, aire atmosférico, refracciones y todos esos efectos que ya como que lo estuvimos viendo. Entonces,
At the center of the image.
según él
Look
había
how
una curva, no
flat
sé,
it
yo no
is,
vi nada de
just
eso. Yo veo un plano
incredible.
nomás.
And we can do some interesting analysis here. By knowing the altitude, we can get a distance to the horizon of about
Claro, él
205
calcula lo negro como la
miles, okay,
curvatura y
from
sigue plano después atrás.
the globe model. And then we know our camera's field of view of about 38 degrees. So then we can calculate what the visible horizon length is. And that came out to 136 miles. Okay? Now, on a globe, 136 miles produces a curvature of 1.97 degrees. And to illustrate what that would look like, up at the top, I have that dotted line at 1.97 degrees, and I calculated that just based on the pixels. And then I drew the white solid line, and I tried to get it so it bisects the angle, because half of the angle is on one side, half the angle on the other one. So it roughly comes up to about half the distance in the center. And so we get a feel for the curvature. So obviously it should be quite noticeable. But as we can see in the image, it is extremely flat. Now, obviously, I could have taken all my photos with the horizon in the middle of the image. And I thought about that, but that would be a waste of vertical field of view. I wanted to really get a nice view of the surface, close in and far away.
Tiene razón en eso.
So now let's take a look at the image analysis that I've done. So I've corrected the two images. You see there, layer 1 and layer 2. And then I switch visibility back and forth and observe how the features move on the ground. And then I put markers so I could know where they're located, right, and the distance. And we can see that objects in the foreground move more than objects in the distance. And then later, the next step is to measure what those distances are of the red lines that I put down. Next, I started measuring the pixel width and the drop from the horizon for each one of those lines, right? And using this data, then I populated a spreadsheet with all these values. And Ideally, all these lines should be aligned along a certain direction, but they're not. I'll show you a graphic shortly. But here, I'm just putting in the vertical and horizontal pixels, and then we'll derive a distance later from the analysis I described. So, fairly simple procedure. Something to point out, the flight direction was slightly, as shown there, just deduced by the motion. So I actually pointed my camera slightly forward, okay, to avoid seeing the turbofan engine. And that's why the lines are slightly sloped. And ideally, we kind of want all this measurements along the straight line. So there's some projection, slight mismatch in projection there, but I wanted to highlight that. So here's the corrected images, and I left a little bit of curvature. I could have been more aggressive with the barrel distortion correction, but I left a little bit in there because it really doesn't make that much difference, because we're really looking after the horizontal displacement. So this technique is a little bit resilient against barrel distortion.
Sí, el lente que usa, yo lo conozco y es verdad, tiene distorsión de barril, no, es buena calidad y toda la definición, pero tiene esa pequeña que a nosotros eso no nos afectaba porque grabamos escenas, cosas así de ambiente, entonces no, pero para hacer un trabajo así de horizonte te va a afectar.
That's really good. So we need the time when these images were taken, and that's stored with the image there. And unfortunately, I didn't widen that enough to see the actual time, but it records it down to the seconds. And we'll use that time difference in the analysis. Before we get in the numbers, let's have a look at Google Earth, just for comparison. Obviously, different model than reality, and we can perceive that curvature. It's quite obvious, and sometimes we have to be at a higher elevation or much closer to get the right perspective, or close to it. We cannot match the full perspective because reality is different than this globe model that we've all been, told about and educated, from a young age. I mean, none of us rationally thought about some of these proofs that we live on a globe. We just accept it, it's just passed down through generations. But reality is a little bit different, and our technological gadgets and sensors now are beginning to illustrate a different reality of our world. Quite fascinating. Now let's have a look at those gory details, numbers and equations. So here's my spreadsheet. So I've entered the horizontal and the vertical pixels there, and then I can calculate a magnitude in miles, and there's my equation. K13 on the right, baseline distance, that's the right from the time, and then I have these adjustments, horizontal pixel adjustment and vertical, just to fine tune, just in case I didn't pick the correct horizon. Of course, the pitch of the camera, I translate everything into an angle, and then I can get that magnitude in miles. Now, here is the equation for the baseline, as you saw, and it's dependent on the time difference there and the velocity, and I adjust a little bit the velocity and the horizontal pixels. Those are the three variables that I adjust to kind of fine tune. You'll see the surface is sloped a little bit. Now the angle, I use the A tangent function here because produces a little bit more accurate results. We're dealing with larger pixel numbers. So the same thing, we use the pitch of the camera, and 30,000 is the focal length in microns. And of course we convert to
No sé por qué dijo micrones y en
degrees
milímetros.
from radians. Now the horizontal and
Es lo
vertical
mismo, parece
distance
que
are very simple,
se
right? It's
traduce,
d5.
creo.
There, the d column, which is the magnitude, the slant range, times the cosine, and the other one, this vertical, is times the sine, right? It's a triangular formula. This graphic helps us understand the geometry. So we got a slant range and an angle, right? Magnitude and angle. That's a vector. And there's a green triangle there composed with one of the red lines. And we use trigonometry to get the height and the ground distance in the coordinate frame of the image, which is why I have that vertical adjustment in angle, so I can lift and rotate the coordinate system up a little bit, and that rotates the surface, but the surface still comes out extremely flat, which is quite incredible. So yeah, simple trigonometry. Now, let's continue. So what I've done here, I've taken the average of the vertical height and the standard deviation. So we're calculating how much the surface drops relative to the aircraft. And that comes out to about 29 feet, just incredible accuracy there. And also the aircraft elevation is computed from that with the equation you see there. So it comes out to about the altitude we were flying at. Now, we need to calibrate. I wanted to rotate the image correctly. So I picked this calibration point based on the Danish Alps reservoir, and we'll look at that in a second. It has a width of about 17 something, whatever that number was there. And here's the equation, the same as the ones above. And I get a distance of 26.6. So that's how I determined how far away the aircraft was from the reservoir. And then I interpolate from the data right there. See, I interpolate between those two values, and I put that in there. And then for the second calibration, that's different. That's based on the distance to a feature on the ground. And I'll show you that in a second. So I use those two calibration points to kind of anchor the image, because otherwise the image comes out slanted. Now there's two more equations at the top for the horizon, since I'm moving the pixels up. So that one, there's the formula for it. It's based on the altitude. Okay, and the line below is based on extrapolation from the two previous lines. As you see on the left, extrapolate there. And I actually match those two things. They have to match. So that was another optimization technique. Now here's the incredible result, folks. Look at that. This is crazy. We're picking up a little bit of a curvature there, but in Google Earth I studied it. The surface does begin to go upwards because it's a river that's flowing, right? And it flows downhill. So it lifts up a little bit, but look at that drastic drop, right? The curvature of the Earth drops away much faster. And here we're just zoomed out a lot more, up to 750 miles. And really, when I play with this, I could get it compressed about 300 miles or out to 2,000 miles. And it's not really the distance so much here as the flatness. We're interested in the flatness. We know that our view is cut short by atmospheric haze, and there's also refraction in the atmosphere. Otherwise, we would see across the world, you know.
Claro,
But that's not the
esa
case.
desviación del
There's
plano
one
es por los
observable
efectos
reality,
ópticos, yo me
whether we
imagino.
believe in a
Es
globe
lo que está
model
diciendo ahí, justo él mencionó la
or the flat
refracción y
Earth.
eso.
One uses refraction one way, the other one uses it the other way. But there is something here that is exaggerated, and it's the scale. Let's have a look at a true scale graph. Now, this graph is drawn to scale, and as you can see, the difference is actually much smaller, right, between the globe and this flat surface. Not that drastic. You know, in the top part, we're zoomed out to 500 miles, and we kind of notice the drop there. It becomes quite noticeable. And in the bottom chart, I'm zoomed in because I wanted to show you the constraints, right? C1 and C2. That's what that meant. And those kind of anchor this straight blue line. We can rotate it down or up, but it's still straight. That's the point here. It's still straight,
Claro.
you know. I didn't quite perfectly get those constraints just right.
Ahí como que se alejó de, de los datos, ¿cierto? O sea, como que ahora tiene más distancia. Se nota más el plano, se mantiene recto al final.
You know, change the fact that the observed reality is extremely flat. You know, our eyes are not deceiving us. It is just incredible. It just blew me away, you know. Just incredible stuff, folks. There you have it. The Earth is extremely, extremely flat. We can identify features on the ground. We don't need relative motion to determine our distance. And here's constraint one, how I determined that I'm 26.6 miles away. So there's this reservoir there, and we can measure its width, as we've seen in the infrared image. It shows up. And then I have another constraint number 2 up here, that I've also measured this farm, this slanted road. So I've used those to kind of hone in on those plots of land. Notice they're green, so on infrared it's white because there's a lot of vegetation and stuff. And I've done a detailed analysis to actually anchor those 2 points down. So here, what we're going to do is we're going to measure the width of this reservoir. And let me set that to feet. And I know it's obviously slightly approximate, but around 1780. I don't know, you would take a few feet there. But now that we know that distance in the image, that's equivalent to a certain amount of pixels, and we translate pixels into an angle, knowing the pitch between the pixels and the focal length. So really cool analysis, and we use that now to get our distance of 26 miles. So, is the Earth flat, or does it only appear to be flat? Now, we're not the only ones to know about this phenomenon, and they patch up the globe by saying there's downward refraction. As you can see in this chart, the red line is the light path.
Refracción hacia abajo, eso lo vimos. A él le dijeron que, claro, si viste, los globertos usan ese de refracción hacia abajo, ¿viste? Y ese destruye el que mostré, el de los barcos flotando. ¿Vieron? En el video pasado le expliqué eso. Y la señora Berguquina, la de hierofantes del globo, también la usa hacia arriba, la usaba. Levantaba la refracción, los barcos de la curvatura los levantaba. Le decía, cuando te encuentres con el globerto profesional sabe que la inversa no funciona y que la refracción normal es la que usan ellos.
I will leave you with this incredible 3D image. Grab your glasses and enjoy, folks. The Earth is extremely flat.
Me despido con esta y nos vemos la próxima.